We shall now start a very short discussion on the ARM instruction set. Now, you shall see later as part of this course, we shall be showing you a lot of demonstration on some ARM based boards and also some Arduino boards. There we shall be writing our programs in a higher level language, but here in this and a couple of other lectures we shall be discussing about the low level features of the ARM processor, and for that we need to have a basic idea about the assembly language features that ARM architecture provides. So, the title of this lecture is ARM instruction set, the first part of it. Now, here we shall be broadly talking about the various categories of ARM instructions and in particular the data processing instructions that are provided by the ARM instruction set architecture. Okay. Talking about the ARM instruction set, you see, as a developer you need to develop or design an embedded system. You will be having a hardware platform, a microcontroller based system, and you will have to write a software for it. Today, most of us develop this software in some high level language, either in C or in Python or in Java, in some language like this. But it is always good to know the lower level features of the processor in order to have an informed decision that which processor may be better for a particular application. Okay. So, it is with this motivation we are giving you a brief introduction to the assembly language features of the ARM processor, which is a reflection of the hardware features that are provided by the ARM platform. Okay. So, broadly speaking, well, any instruction set, not necessarily the ARM instruction set, they can be categorized into various groups or broad categories. So, in ARM, let us define these categories as data processing, data transfer and control flow. So, the instructions which are there, they can be categorized or classified into one of these three types. Let us try to understand. Now, in a microcontroller, I have said most of the modern microcontrollers, not the first generation ARMs, the subsequent ones, they are based on the Harvard architecture. So, you will be having a separate program memory and a separate data memory. So, the instructions which constitute the program, that will be stored in the program memory, while all temporary data which you will be manipulating on will be stored in the data memory. So, among the registers, this program counter is one register which will be pointing to the address of the next instruction in the program memory, right. So, whenever a new instruction is brought or fetched from memory, it will be fetched from the address which is stored in the program counter. So, when I am talking about the data processing instructions, we are talking about carrying out various arithmetic and logic operations on data. Now, ARM is based on the RISC philosophy of architectures. Most of the ARM features are RISC based, reduced instruction set computer based. Now, here all data processing instructions, they operate only on registers. They work only on registers. That means, when I say add, we will be adding the contents of two registers and storing the result back into another register. So, memory is not coming into the picture here at all. Okay. Now, when we talk about data transfer, here there are options. We can transfer from one register to another, or we can transfer from register to data memory, or data memory to register. So, these options are all there. These will constitute data transfer instructions. And control flow instructions are those which will alter the sequence of execution of a program. Normally, as I said, program counter will be pointing to the next instruction to be executed. Now, as the instructions are executing, the value of the program counter gets incremented consecutively. But whenever you have some instructions like jump or a subroutine call, suddenly that sequence will be disturbed. You will be going to some other address, and from there you will be starting to fetch your instructions, right. So, this is what is meant by change of control flow, and such instructions are termed as control flow instructions. So, essentially control flow instructions are those which will be altering the value of program counter in some way, so that the normal sequence of instruction execution will be altered. Okay? Fine. So, we first talk about the data processing instructions that are present in the ARM instruction set. Now, in the ARM instruction set, the first thing to note is that the registers are all 32-bit in size. The arithmetic logic unit which is inside the processor, that also has the capability of operating on 32-bit numbers. Okay? So, all operands that are being operated on are 32 bits in size. This is something fixed in ARM, and these operands can be either registers. So, you may carry out these operations on registers, or some of the operands may be constants. These are called literals or immediate values. I may say add the value 10 to the content of a register. That 10 is like a constant, that is called a literal or an immediate value. That value 10 is specified as part of the instruction, that is called immediate operand, right. And the result after the calculation is also a 32-bit result, and this will be stored in some particular register. There is of course one exception. There is a special multiply instruction where the result is stored as a 64-bit number. Now, you know, whenever we multiply two n-bit numbers, the result can be twice n bits, the result can become double in size. So, when you multiply two 32-bit numbers, the result can be maximum 64-bit in size. So, there is a version of multiply instruction where the result can be stored in two registers 64 bits. This is an exception. Okay? And the other thing is that all operands and the result registers that we use in an instruction will be specified as part of the instruction. Now, in these lectures we shall not be discussing about the instruction encoding, that means exactly how the bits of the instruction word specify the registers. We shall not be going into that detail of the architecture, but essentially what kind of instructions are supported, those we shall be discussing. Okay. First, let us talk about the arithmetic instructions. Well, arithmetic instruction, the most basic instructions are addition and subtraction. So, ARM provides with various addition and subtraction instruction alternatives. Let us see what kind of instructions are there. First is a simple add instruction. Well, here as an example I have shown three registers R0, R1, R2, but you can have any registers here, not necessarily only R0, R1, R2. The first one represents the destination, the second and third indicates the two source operands. So, when I write add R0, R1, R2, the values of R1 and R2 will be added and the result will be stored in R0, right. There is a version add with carry which is normally used to handle multi-precision arithmetic. So, when you are adding two 64-bit numbers, you add first two 32-bit numbers. If there is a carry, the next 32-bit numbers you will be adding with that carry. So, you should have an add with carry version of instruction. This is add with carry. Here what it does, same thing, it adds R1 and R2 with carry. If the carry bit is 1, then an additional 1 will be added. If the carry is 0, then nothing is added. Then there is a normal subtract instruction. This is R1 minus R2, result is going into R0, and there is a similar borrow concept in subtraction for multiplication arithmetic again. So, there is a subtract with borrow version SBC it is called, where the carry flag is used. Now, the actual calculation is done like this, R1 minus R2 plus C minus 1. This takes care of the borrow during subtraction operation. Okay. Now, there are two variation of the subtract instructions where the role of the operands are reversed. Like here sub instruction we are saying R1 minus R2. Now, if I say RSB, this stands for reverse subtract, this means R2 minus R1. Similarly, there is a version with borrow, reverse subtract with carry. So, it is R2 minus R1 plus C minus 1. Now, you may ask why you need two kinds of subtract instruction. I can always write this instruction as, let us say, subtract R0, R2, R1. I can always write like this. Why I need another RSB instruction? The need is that we shall see later, I have not talked about it. This ARM instruction allows the second operand to be specified in more flexible ways. Like this second operand R2, this can be specified in multiple ways. So, if you have a reverse version of subtract, then that flexible operand can be subtracted from, or the normal data can be subtracted from that flexible operand. Both ways you can have. So, we shall be seeing what kind of flexibility the second operand provides you, but this reverse subtract allows you to add a normal operand from a flexible operand, or from a flexible operand you can subtract a normal operand. Both options are provided. And in these subtract instructions, you are viewing these 32-bit numbers as either unsigned or as 2's complement signed numbers. Now, with respect to addition and subtraction in binary, these two make no difference. The way the arithmetic is carried out is exactly identical. Okay? So, they actually mean the same thing. All right. So, after this addition and subtract instructions, there are some bitwise logical instructions. There are instructions like AND, OR and exclusive OR. So, when I say AND, let us say similar to add R0, R1, R2, what happens? R1 and R2 are the two operands. So, they are all 32-bit numbers. Okay. Let us say this is R1, this is R2. So, the last bit of R1 and R2 are bitwise ANDed together, and the result is stored in R0 in that corresponding bit here. Similarly, the next two bits are ANDed together, the result will be stored here. Similarly, this bits and this bit are ANDed together, result is stored here. This is called bitwise logical operation. So, I can do AND operation, OR operation, or I can do exclusive OR operation. These three instructions are supported. Now, there is another instruction also which is supported at the bitwise level. This is called bit clear instruction, in short BIC. So, the actual meaning is the register R1 is ANDed with the complement of R2. You take a NOT operation and then do an AND. So, that in R2 whichever bit is 1, if you do a NOT, those bits will become 0. if you do a AND with R1, those corresponding bits of R1 will become 0, because AND anything AND 0 is 0. So, actually because of that this is called a bit clear instruction. So, wherever in R2 you have 1, those corresponding bits in R1 will be made 0, that means those will be cleared. That is why this is also called a bit clear instruction. Okay, fine. Then you have some register to register move instruction. Okay, this also we are defining under the data manipulation instruction category. Now, here there are two kind of register to register move that are supported. One is a simple register to register move. You see, when I am saying move a register to a register, I need to specify only 2 operands. Just like the other instruction we have seen where 3 operands are required, here we need only 2. Okay. So, when I say move R0, R2, it means the value of R2 is copied into R0. Okay. And there is another version, move negated. That means, if I say MVN R0 and R2, here this R2 will be complemented, the not of R2 will be moved into R0, right. So, there are many applications where this negated value of a 32-bit number is required. So, there you can use this MVN instruction, move negated, right. Now, here in the encoding, as I said that you do not need 3 registers, this R1 which we are mentioning earlier, the middle operand, that is not required here, only 2 operands are required. Now, there are a variety of compare instructions. Now, you recall in the program status word current and the saved program status words that we discussed in our previous lectures, there are some condition flags. You recall there were a 0 flag, there were a sign flag, there was an overflow flag and so on. So, these flags actually keep track of the results of some arithmetic or logic operation. When you add 2 numbers, these flags will keep track of the fact whether the result was 0, whether the result was positive or negative, or whether there was an overflow that took place because of that operation. Okay. Now, sometimes you just need to compare 2 numbers and take a decision. You do not, you are actually not doing addition and subtraction and storing the result somewhere, just you need to compare 2 values. So, there are a host of compare instructions available, like you can say simple comparison. You compare R1 and R2, and that means internally you are actually doing R1 minus R2, you are subtracting and you are checking whether there is 0, negative or positive. So, accordingly the flags will be set. There is another version, compare negated, actually it means you do R1 plus R2 and then set the flags, result of addition of the 2 numbers, but you are not storing the result anywhere. This is the difference between a normal add and subtract instruction and the compare instruction. Here these instructions do not produce any result in any register. This is what you should remember. It only sets the condition flag so that you can use that result later. Depending on the condition flag, you can take some decision, right. Similarly, there is a test kind of a comparison. This comparison means you are doing logical AND, bitwise AND of R1 and R2. Then you are checking the result is 0 or non-zero, whatever, then accordingly you set the flags. Similarly, you test for equality, test equal. Equality means exclusive OR. You say exclusive OR, you note one property. If you take the exclusive OR of 0 and 0, the result is 0. If you take exclusive OR of 1 and 1, that is also 0. But if you take exclusive OR of 0 and 1 or 1 and 0, this is 1. So, the result of an exclusive OR will tell you whether the bits are equal or they are not equal, right. So, if you take XOR of entire 32 bit numbers and see the result is 0, this means that the two numbers are equal, all the bits are giving XOR value of 0, that is why the result is 0. Okay. So, these instructions, as I told you, they affect the condition codes, carry 0, this sign or negative flag, overflow, these are stored in the current program status register. There are ways of specifying immediate operands. Like as I said, you can specify some immediate data, like I can write like this with this hash symbol, I can use the second operand as an immediate operand. I can write R2 comma hash 2, this means R2 will be added with the constant 2. I can write subtract R3 hash 1, that means R3 minus 1. Okay. Like this I can add an immediate operand as my second operand of an arithmetic or logic operations. Like for example, if I say AND of this, what does this mean? Okay, hash, as I told you, hash indicates immediate operand, and this ampersand indicates that the number I am specifying is in hexadecimal. So, when I do AND with 0f, what does that mean? 0f in 32 bit means 000f, and f means what? 4 ones. So, if you do AND, only the last 4 bits of the number will remain, all the others will become 0. So, actually what you are doing, this R4, the last 4 bits I am showing like this, bit number 0 to 3, these 4 bits are copied to R6, the remaining bits are all made 0, right. So, with respect to the immediate values, well, there is of course some restriction of the range, maximum value of this number you can represent. So, the range is typically 0 to 255, you can also regard it as a 2's complement number, you can give a negative value also. And there is another facility, there are additional 4 bits in the instruction where you can specify that these operand value will be rotated, and means within that 32 bit range, these 8 bits can be positioned either here or here or here or here. So, you can make your number as per your requirement, and then you can do add, subtract and whatever you want. So, that bit position is some multiple of 2. I am not going into detail, but it has some flexibility in that. You can specify that where that immediate data will fit in inside that 32 bit number. Okay. Then I talked about some flexibility in the second operand. You see here this shifted register operand comes in. You recall in the architecture I told in ARM there is a barrel shifter. The second operand optionally goes through the barrel shifter, you can shift it and then you can do some arithmetic or logic operations. So, in the assembly language level also you can specify like this, you can specify add R1, R2, R3, and in the fourth parameter you can say logical shift left hash 3, that means 3 position. This actually means the second operand is shifted left by 3 positions and then added to R2. Okay. So, you can specify this as a constant, how many bits you want to shift, or you can also specify some register, logical shift left R5, whatever is the value in R5, that many bits will be shifted. Let us say if R5 is 20, then it will be a 20 bit shift. You see here like this, R3 is shifted left by whatever is the value of R5, that many positions. Now, you see here we have a facility of specifying the second operand in some flexible way, either in the normal form or in some shifted form. That is why this reverse subtract operation you recall, there I can subtract a register from the shifted value of another register. That is why this reverse subtract facility is also there. Okay. And not only logical shift left, there are various shift and rotate instructions or options available: logical shift left, logical shift right, rotate right. Rotate right means when you shift right, the last bit coming out will again get inside the register, that is rotate right. Rotate right extended means the register you are rotating right, then there will be your carry flag. This bit will go into this carry flag and the carry flag will get rotated in it. That is why this is something like a 33 bit rotation. This is called extended by 1 bit. And arithmetic shift left is same as logical shift left, no difference. And arithmetic shift right means if it is a negative number, when you shift right, 1 will be added to the most significant bit side. If it is positive number, 0 will be added. These are the various options. So, in this diagram some of these are shown. You see here, if you say logical shift left 5, the original register will be shifted left by 5 positions and zeros will be added on the right. So, if you say logical shift right by 5 position, similar, you shift right and zeros get added. Now, if I say arithmetic shift right, but the number is positive, which means the MSB was 0, then zeros will be added. But if the number was negative, which means most significant bit was 1, then ones will be added on the left side. And rotate, as I had said, whatever goes out, rotate right, whatever goes out of the register, this will be getting inside here. So, you are rotating. And rotate extended means along with the carry flag, as I had said, it will be a 33 bit rotation. Okay. These are the various options. Now, there are some multiplication instructions also. Multiplication in the simple form is R1, R2, R3 like this only. So, you multiply the two numbers R2 and R3 and you take only 32 bits of the result, because multiplication result can be 64 bit, but you ignore the high order bits. You assume that the result is fit, the result will fit within 32 bits and you take only the last 32 bits. Okay. And in multiplication, immediate operations cannot be used, only register operands. And there is another instruction which is very much useful for digital signal processing or DSP applications. This is called multiply and accumulate. There you need to continuously multiply a number with some other number and add to another value continuously. So, here this multiply accumulate instruction will have 4 register operands, and the meaning is you multiply R2 and R3 and add it to R4. So, not only multiplication, also an addition, and you take the last 32 bits of the result. And as I said, a 64 bit multiplication version is also available, which we are not discussing right now here. Okay. That is also available. So, with this we come to the end of this lecture, where we have talked about some of the arithmetic and logical instructions which are available and supported by the ARM instruction set architecture. In the next lecture, we shall be talking about the data transfer instructions. What are the various kinds of data transfer instructions that can be used to transfer data between registers and memory? Thank you.